background knowledge on what we're going to do today, we have to talk about a force called lift. That's your link to the next slide, okay? Why is this thing not working? So lift is produced whenever we have an airflow flowing around a control surface. It's a very important force because it can be manipulated by the pilot to maneuver the aeroplane. So that second click there brings up that summarizing point, the force that can be used to manipulate the aeroplane. So I like to say that when there's an airflow going around the control surface, it produces this force, okay? So tell a little bit of a story as you go through it. To expand on lift a little bit more, many years ago there was a scientist called Bernoulli, and he he studied fluids, fluid mechanics to be precise, and he developed a theory of the behavior of fluids, and it was pressure energy plus kinetic energy equals a constant. So pressure energy is the static pressure or the ambient pressure of a fluid, and the kinetic energy refers to the energy of speed, or what we can also call velocity. And a constant means that there is a constant amount of total energy, as in these two types of energies are transformed to keep the total amount the same. In order to prove his theorem, Bernoulli used a special type of pipe, click, and that brings us up, called a Venturi tube. It's a pipe that has a narrowing or a constriction through it. And he passed a fluid through it, and he measured its pressure and its velocity at different places in the fluid. So let's start off with the first set of values here. Perhaps near the beginning of the pipe, he found that the velocity was 40 units and the pressure was also 40 units, giving a total value of 80 units of energy. As the fluid got to the constriction or the narrowing, he noted that the velocity or the speed increased, but at the same time the pressure reduced. But the total amount of energy remained the same, in this case at 80 units. After the constriction, the energy values changed again. The velocity reduced and the pressure increased, once again maintaining that total of 80 units. So what is being shown here is that the total energy is being conserved and pressure and velocity is being transformed from one type of energy to the other in accordance with Bernoulli's theorem. Some everyday examples, that's a step I like to do now. You guys tell me what are some everyday examples of Bernoulli's theorem. They won't know probably, but you guys will, or should.
Garden hose.
So talk through the hose. You did say hose, eh?
Yeah.
So if you put your finger over the end of the hose, you're constricting the flow of the water, and the velocity of it, the speed at which the water comes out of the hose increases. That's an example. Give me another.
Rapids in a river.
Rapids in a river, yep. Any others? Good. You don't have to mention that one. I do like that one though, because it's about the pressure as opposed to the velocity, whereas the hose in the rapids is like more about the velocity. So you don't have to say every example that you can think of, but have that one up your sleeve as well. Good. So you know plenty of them, so that gives it some practical stuff to it. Now, why do we even care about this? How is this even relevant to us in an aeroplane? Well, firstly, the fluid that we're interested in an aeroplane is air. So fluids are liquids and gases. Air is the gas that we fly through, and it is essential for the production of lift. Now, if we have a look at the surface of the Venturi here, we'll note that it actually looks a little bit like a control surface or an aerofoil, like here. This is an aircraft wing, which we can call an aerofoil. An aerofoil is just any surface that produces lift, and the control surfaces of the aeroplane are also examples of aerofoils. So the air that flows over and around a wing actually behaves just like a fluid when it flows through a Venturi tube. So that's your link to how is Bernoulli's theorem relevant to the aeroplane. You kind of should be thinking, oh yeah, this sounds a bit like the start of a lift package, right? Maybe a much more simplified version of the lift package. Very simplified. We don't need to go into the whole Bernoulli's theorem. That would be totally irrelevant to a new student. So to expand on that a little bit more, here's an aerofoil. In this case, it's a wing, and to it we have hinged a control surface, and this control surface can be moved by the pilot to manipulate lift and control the airplane. So imagine we're out flying, we've got a fast moving airflow approaching the wing, and as the airflow meets the wing, some of the air will pass above it and some will pass below it, like this. Now, even though we can't see it, there is a constriction being created above the wing. There's no visible cap that we can see here, like in the Venturi tube, but there is a cap nonetheless, we just cannot see it. Now notice how the wing here is more curved above than it is below. So this means that the air flowing over the wing is going to accelerate more than the air flowing underneath. Now here's where I ask a question. So what happened to the pressure when the air accelerated through the Venturi tube? Oh, yeah, it reduced. So where are we going to get a bigger reduction in pressure? Ask the student. Oh, it'll be on the top. So we have a relatively high pressure underneath the wing and a relatively low pressure above the wing, and this gives rise to a force called lift, which acts in the direction of the lower pressure. And one click brings up the vector. I'll give you a moment to write. Sorry, I think I might be running a bit too fast for you. Pause for a moment. So take note that everything I'm saying is as simple as possible, okay? There's no full version of Bernoulli's theorem because that's disgusting and irrelevant. We just want practical. I even wondered, do we even introduce Bernoulli's theorem in this briefing? Maybe we introduce it later on, but no, it can be done here with good effect. It's not an information dump aid, like I said back at the start. It's not an opportunity for you to shout out everything that you know about lift and Bernoulli's theorem, because that will actually do more damage than any good. Okay, so I'm now going to introduce you to some terms that we use. And you'll hear these terms come up time and time again in these maths briefs and all the other discussions that we have. Every time we draw an airfoil, we don't want to have to keep drawing airflows above and below. So we tend to simplify the airflows by drawing in a relative airflow. So the relative airflow is illustrated on the diagram here now, and it's how the airflow is presented to the wing. Now if we draw a line, a straight line, from the front, or what we call the leading edge of the wing, to the back, what is known as the trailing edge, we get the chord line. And the angle between those two, the relative airflow and the chord line, is known as the angle of attack. Now it's not shown on here, but there's another term I want to introduce you to, and that is camber. Camber is the curvature of a aerofoil or a control surface. If we were to draw a dotted line or a line equal distance above and below the surfaces, we get an idea of what the curvature of this aerofoil will be. And different aerofoils have different or varying amounts of camber. And when we change the deflection of a control surface, we also change the camber. So why do we care about this? Is because camber and angle of attack are two of the ways that a pilot can manipulate the lift on a control surface to control the aeroplane. And that's achieved by deflecting the surface. Now there's one more way that lift can be manipulated, and we've already talked about it already, and that is speed. So because you've already talked about how through a Venturi the airflow speeds up and that leads to a lower pressure, just ask a question here to gauge, have they understood it? So what do you think would happen if we flew faster? What do you think would happen to that low pressure region on top of the wing? Hopefully they say the line, something along the lines of, oh, it would be even lower pressure, or it would get bigger, something along those lines. So the difference between the higher pressure below the wing and the lower pressure above gets bigger, and lift is dependent on that pressure difference. So summarize what they've said with that statement. And that another click brings that up. So it's quite important for you to actually say to them, why do they need to know all of these terms? It's because these are the things, or the ways in which lift can be manipulated. So to expand on this a little bit more, let's show now what actually happens to lift when we deflect a control surface, and we'll kind of compare this diagram here with the one on the previous slide. So here we've got an aerofoil, the wing again, and we've attached a control surface to the end of it, and the pilot has deflected it down. So let's take a look at what's happened here. So once again, there's our chord line, straight line from leading to trailing edge, and we know that when the airflow meets the aerofoil, some air goes above and some air goes below. And let's simplify that and resolve it into the relative airflow. What have you noticed has happened to the angle of attack? Ask your student that. Hey, it's a lot bigger than the angle of attack on the previous slide, isn't it? And this means lift will increase. And this increase in lift can be used to maneuver the aeroplane. Now, it's not the only thing that's changed. That camber has increased as well. So that mean curvature, if we were to draw a line equal distance above and below, that's also increased. So that also means lift has increased. And this will be used by the pilot to maneuver the aeroplane. So it's just talking through that process. There is only there is only a slide showing the control surface deflected down like this. There isn't one showing an up deflection. It's not necessary if you think about it, because it's just the opposite, isn't it? So just make sure you mention that. So the opposite would happen if we deflected the control surface back up again. Well, that angle of attack would reduce and the camber would reduce, so the lift would reduce. Don't forget that step. That's particularly important when you get to the use of the ailerons, because of course there's two of them, one goes up and the other goes down, and the movement of those is how you actually achieve the load. So talk through that process there. Now, how do we actually manipulate this lift force? What are the controls that our aeroplane has now? If they've got previous flying experience, just ask them, okay? Otherwise, you'll go through each of these. And they do come up click by click, but you just as easily just talk about it. So we've got an elevator, which is on the trailing edge of the horizontal stabilizer up here in green. We've got ailerons, a left-hand aileron and a right-hand aileron, which are on the wingtips. And we've got the rudder, which is on the trailing edge of the vertical stabilizer. Now this is where the briefing gets really easy if they've got previous experience, because all this next stuff is on the primary effects and how to move the controls. So you have to have asked those questions. So let's take a look at what each of those controls actually does when we maneuver them. So the aeroplane has 3 axes of rotation, one for each of the flight controls. What else could you say about that? I suppose mention that they all pass through an axis is an imaginary line about which the aeroplane can be maneuvered or rotates, and they all pass through a common point. That's all I'd say about axes. You don't need to say they go through the center of gravity, okay? Just that they pass through a common point. So here's one axis. We've got the lateral axis. It goes from wingtip to wingtip, and when the aircraft maneuvers about this axis, we call it pitch. So another click brings up this box here. Another click will display the animation. So using the elevator, we can pitch the nose up like that, and we can pitch the nose down like this. We're not talking about what we're doing to the stick here, okay? We're just talking about the control and what it does to the nose. So what the elevator really does is it changes something called the attitude of the aeroplane. And this is the position of the nose in relation to the horizon. Mention that. Simple, brief terms. So what we really use the elevator for is to control the attitude, and this is going to be used for climbing, descending, and even flying level, which you're going to learn about in the next couple of flights. So I like to add that bit because now the student understands what elevator is even for. If you miss that bit, well, there's no relevance to it. So then you just go through the same process, but with the remaining ones. Another axis we have is the longitudinal axis. This runs from the nose to the tail through the center line of the aeroplane and intersects the lateral axis. Movement about this axis is achieved through the ailerons, and it is called roll. Show the animation. So we can roll the aeroplane to the right, and we can roll the aeroplane to the left. So what do we actually use the ailerons for? To control our direction, to turn, but also to maintain a constant direction. So there's that practical step again. You could use the model here to illustrate the movements. Absolutely fine. I don't see the point because it's illustrated on here, but I'm not going to tell you off for using the model. But if you use the model, remember, as you learned last semester, always align the axis with the student. So if we're talking longitudinal and Diaz is my student, then the axis should be aligned with him and showing it like this. Be careful with your left and right because of course it's back to front for you. Normal axis, hold it like this. Lateral axis, wingtip, like that, okay? Make sure it's clear. Okay, same process for this one. So the third and final axis is the normal axis. Movement about that is called yaw, and it's achieved with the rudder. And what do we use the rudder for? Show that animation there. I'll ask that question to you. This isn't a question to pose to your students, but what do we use the rudder for? Third year students don't know what the rudder's for. What is it for? Carl?
Balancing.
It is, yep. So what is balancing? If you're out of balance, what is happening?
Slip.
It could be slip, could be skid, yep. Do we want to slip or skid?
No.
Nope, it's not a normal way. So what I like to highlight either on this slide or one a little bit further along when you get to the control is the primary effect of using rudder is yaw. That's absolutely fine, but it is not its primary purpose. If you think about it, the primary purpose of rudder is to prevent yaw, isn't it? That's why you use it in a turn. You use it to prevent adverse yaw. You use it whenever you change power settings to prevent the yaw from the slipstream. That is its purpose. It is not to cause yaw. When do you ever stab in rudder in flight and just use rudder on its own? You never do you? Not unless you're deliberately wanting to slip or skid, which is not a normal thing. So mention that, because the student gets the wrong idea about it otherwise. Okay. There is a high likelihood of you repeating yourself from the previous slide, this one, and the three that come after it. So I really want you to rehearse what it is that you want to talk about on the slides, because otherwise you just say the same thing slide after slide and it's really boring. So now we're going to break those controls down individually and talk about how to move them. So again, previous flying experience, ask them, hey, that Cessna used to fly. How did you pitch the airplane up and down in that? Or if they were flying the airplane with a stick, how did you pitch the airplane up and down in that? So let's talk about the elevator. We're cruising along, let's say, and you ease back on the stick in the DA40. And this will deflect the elevator up, and this will cause the nose of the airplane to pitch up. What I like to do here is use the model to actually show how the force is manipulated to cause the pitch. So if we've deflected the elevator up, this will cause a force downwards, and look what happens. When I push a force there, the nose pitches up. You've just proven that that is what's happening to the elevator. I personally do not like, for this particular one, to talk about how the angle of attack and camber change. I prefer, if you're going to go into that detail, talk about how the airflow is deflected upwards. Because if an airflow is deflected upwards, you'll get an opposite force going downwards. So you're still getting it downwards. What about if we ease forward on the stick? If we ease forward on the stick, the elevator goes downwards and the angle of attack increases on the elevator and the camber increases. So this manipulates the lift. Talk about the direction of the force this time. So this time we've got a force going up. If I push a force there, look what happens to the nose. The nose pitches down. Use this, okay? It's probably the most practical thing to use in this demonstration is what's actually going on with that force. I'm going to talk more about why I don't like to use reduced angle of attack and reduced camber here at the end of the briefing. So then you'd go through the same format with the rest of the controls, okay? So aileron, what if we want to roll the airplane? Now this is achieved by moving the stick or easing the stick left and right. This will move the aileron. So if we ease the stick to the left, this deflects the left aileron upwards and the right hand aileron downwards. Terminology, never say just right, okay? It's always right hand, left hand, right hand. It's the right part that's always a bit ambiguous. It's right hand, not right So then you can talk through the same process, what's actually going on with lift here. So on that left hand aileron, in the top diagram here, the camber reduces, the angle of attack reduces, so the lift reduces. On this downgoing aileron here, the angle of attack increases, the camber increases, so the lift increases. So we've got more lift being produced on one side of the aeroplane, and that is how roll is achieved. So talk through that process. Rudder. So we use the rudder by using the pedals. The additional thing you could mention here, I suppose, is how are those controls actually linked to the cockpit? So what's the answer to that? How's the rudder connected to the pedals? Yep, what about the elevators, the elevator and the ailerons? Push rods, yeah. So you can just briefly mention there, so those control surfaces are connected to the cockpit controls through either rods or cables, depending on which one you're actually talking about. So talk through this process again. I won't present this slide because it's exactly the same format as I've just talked to you. The only thing here, if you haven't mentioned already that the primary purpose of the rudder is to prevent yaw, then say so here. Primary effect is yaw, primary purpose is to prevent yaw though. So that's the end of your primary effects section. This table here, and there's another version of it towards the end of the briefing, if you were doing a pre-flight briefing, it's this table that I would draw up on the board. I would have control, primary effect, how to move the control, secondary effect. I'd have about probably 4 columns, and you can get the student to tell you the answer to each of the different boxes in the column, like here. Because they already know this, right? You've just told them that, so there's no reason for you to explain that again. And at the end of this briefing, there's a slightly bigger table with all of this information in it again. By then, they should know all the answers, so there's no need to keep teaching it. So the secondary effects. We're now going to take a look at what else happens when we move each of the primary controls individually on their own, and take note of what else changes. So let's start with the elevator. What's the primary effect? Oh, yep, they remember that, it's pitch. Now, what is the result of this? Now, imagine you're in a car. You're in your car and you get to the bottom of a hill, you're about to go up the hill, and you don't change your foot on the accelerator. What's going to happen to your speed as you go up the hill? Oh, it's going to slow down. But you're still going to go up the hill, aren't you? So you're still going to climb. Now, the same thing happens in an aeroplane. If you pitch the nose up, the aeroplane will start to climb and the airspeed will start to reduce if we don't do anything. It's the opposite, obviously downhill. So talk through that process. So relate it to something they already know. If they don't drive, then talk about a bicycle. So is there a secondary effect? They won't know, of course. There's not a. So there is no secondary effect. By that I mean the aeroplane has no tendency to start rolling or yawing about its other axes when you use the when you pitch the nose up or down. It just has consequences that your altitude and the speed will change. But it's a bit different when we get to the ailerons. So what would happen if we move the stick to the right? You know, ask them a question like that. Oh yeah, the aeroplane would roll to the right. Now, what's the result of this? The aeroplane is going to slip. Now, some people like to draw a little vector diagram of how slip is created, because if you think about it, we might have discussed how the vertical component of lift is not equal to the weight from last semester. That's complicated for a brand new student, okay? Much easier just to grab a table or something like a table, put that on a bit of a slope. Here's the airplane, flying along, and then we roll. This represents that we're rolling that way. If you're rolling to the left, and what starts to happen now is the airplane slips sideways, downwards like that. Remember, it's still traveling forward, right? So it's kind of doing this. You just can't illustrate that on the table. So it's starting to slip downwards and forwards. Now, the second thing that's going to happen there is what? You guys tell me. So how would you explain that to a student?
So, because like we're slipping to the side.
Yep.
Your airflow is now coming from the left side, causing it coming in, get a bit like pushing on the rudder to make us turn forward. Will you explain?
Yes, you're missing one important part. Why does it not yaw that way? Because if there's a big enough force there, it would, wouldn't it?
So there's more surface.
Yeah.
That-
So
yeah.
what I would say is you've explained the slip, and now the second thing that happens is the aeroplane will yaw in the direction that it is rolling. And the reason for that is because there's a point in the aircraft we call the centre of gravity. And there's much more surface area of the aeroplane behind the centre of gravity. So this means a bigger net force is going to be produced at the back of the aeroplane, and that's going to cause it to yaw in the direction that is rolling. And what will happen next is the aeroplane will enter a low attitude and enter a spiral descent. I like to actually take it through to that because I show that in the flight as well. Now, of course, the student's not going to know those secondary effects unless they've actually done this lesson, so you'll have to walk them through that, all right? So that's the consequence of rolling the aeroplane without coordinating with any of the other controls. And then you run through the same process with rudder. Now, when you talk about secondary effects, they're not secondary effects of the rudder, the elevator, or the ailerons, okay? They are secondary effects of roll and yaw, not the controls themselves. Make sense? So we're cruising along, and let's say you press down on the left rudder pedal gently. You can tell some sort of scenario if you like. What's going to happen next? They're not going to know, but I'm going to ask you guys. Yep, skid. So have you ever gone around a corner too fast in your car and you've felt you're skidding out? Well, the same thing happens in an aeroplane. Then what will happen? Yep, why do we roll?
One wing is traveling faster than the other,
Mm-hmm.
produces more force.
Yep. So model use for this one's quite useful. So sort of elevate the model like that, show you yaw to the left. Now this wing here is travelling faster than this wing, so it produces more lift, and that's going to cause the aeroplane to roll. What else causes the roll? Because it's not just that.
Got the shielding effect on the one wing.
Yeah, so it's important to mention that as well. Up to you how you do it. A blue pen or a ruler might be good. You might have to sort of elevate the model like this. So the airflow always comes from straight ahead like this. We've yawed, and the airflow is now meeting the aircraft wings like this. And it's creating, sorry, I put it on this side. It's creating a shielding effect. So this little triangle you can see there is no longer producing any lift, which means that this wing's producing more lift, and that is going to cause it to roll in the direction that it is yawing. So just summarize by going through that process again. We press down on the rudder pedal, the aeroplane yaws, it then skids, and then rolls in the direction that it is yawing. Once again, this is a consequence of using that control on its own without coordinating it with the rest of the controls. So then you come to your summary. Why should a student know about this? Why should they know about this? It's a question for you guys. Why do we care? Because every single lesson from this point onwards involves preventing those undesirable effects. These secondary effects, remember, are undesirable. When we roll, we don't want to start losing altitude and end up yawing. When we yaw, not that we ever do that, when we yaw, we don't want to skid and then start rolling. That's not how we fly, right? So we teach them about the stuff so that in future lessons they can learn to anticipate these effects to avoid them because they are undesirable. You must summarise with that statement in there somewhere. Up to you whether you mention this next point here or whether you do it in the pre-flight briefing or just in flight, but I point out to them that that slip and skid is actually quite hard to, or impossible to see and feel in many aeroplanes. It does happen, we know it happens, but they're not going to see or feel that slip and skid. What they will see though is that secondary effect, that Euro roll is obvious, okay? So that's that table completed. Now you move into aircraft management. There are a few new concepts you want to introduce to your student here. Temperatures and pressures. If you just press one more click, it brings up this diagram here. Introduce to them that, like in their car, the aeroplane has a range of gauges and the engine has some normal operating ranges, which is nice and easy. It's in the green range. Now, things really go wrong, but it's important as a pilot to monitor that the engine instruments are indicating normally. For the first couple of lessons, the instructor will take care of that, but if you ever see anything's not in the green range, I just want you to point it out to me, whether that be on the ground or flight. Something like that is satisfactory for this early level of their experience, but it's important to start developing their awareness that, hey, that stuff is important. And we'll learn how to deal with any problems over the course of your training. Now this next bit, the transfer of control, is probably the most important thing to get right in this briefing. So if it's not, then it'll have a flow-on effect. So there'll be times in every single flight where the instructor will be flying, and you as a student, you'll just have your hands and feet lightly on the controls to follow through with what the instructor is doing. There'll also be times where you are the one flying the aeroplane, and you'll be manipulating the controls, and I may have just my hands and feet lightly on the controls. And then there's another scenario where I won't have my hand on the stick or my hand on the throttle, and I will just sit back and watch you control the aeroplane. So it's important to actually tell the student that this is how every single lesson actually goes. There'll be things that you direct, there'll be things that you demonstrate, there'll be things that you analyze, and who is in control changes at each of those times. So it's really important that we know who is in control of the aeroplane at all times, and there should only be one person in control. And we have this little challenge in response, this I have control, you have control, to make sure we do know who's in control. So let's say I am in control of the aeroplane and I am now ready to transfer the controls over to you. I will say you have control. At this point, if your hands and feet are not already on the controls, you will reach for them. Once your hands and feet are on them, then you will say, I have control. Now we know that transfer has happened and you are in control of the aeroplane. Now suppose you want to give the controls back to me, you will say you have control. I will reach for the controls, and once my hands and feet are on them, I will say I have control. So just talk through that, okay? It may seem really obvious, but remember you've got to think as if it is a brand new student who doesn't know how this works, right? What's really important is at no point should you just let go of the controls. Okay? What I never want to see, particularly from, well, I don't want to see this from any of you, but particularly my 3 students, is when you say you have control, you do not take your hands and feet off the controls until I am reaching for them or have my hands and feet on them, okay? Because in that moment, no one is in control of the aeroplane. And if they haven't trimmed the aeroplane, the nose is going to do that, and I've seen that happen before, okay? So really important, proper transfer of control. Human factors and airmanship, because this is the second briefing, you could ask them, hey, do you remember what human factors and airmanship's all about? Well, you know, airmanship's about good behaviours, keeping yourself safe, good attitudes, setting good habits. Human factors is about keeping ourselves in a fit psychological and physical state to handle the flying environment. And you remember what are the things you've got to think about to make sure you're safe to fly, you know. You don't have to go back through the whole I'm safe thing, but ask them, hey, what does the S stand for? And they might say sleep, you know, rather than stress. So you're highlighting again that you want them to think about this before they come into flight. Motion sickness, I talked about this on the previous briefing because you know you're not going to get motion sick taxiing around on the ground, but motion sickness for new students is reasonably common. So make sure you just ask them, if it's a one-on-one briefing, that's fine. You know, just ask them, hey, are you prone to motion sickness? If it's a class briefing, I wouldn't say do that because you know no one wants to own up to that in front of the class. That's something a bit more personal. But just reassure them that, hey, this is quite normal. A lot of students actually do feel motion sick in the early days, but with regular flying, you'll find it does get easier. And we'll only fly on relatively nice days until you're a bit more experienced. But if you do feel unwell at any stage, don't hesitate to tell me. We've got air conditioning, as you learned in the last flight. You can always come back and land early if we need to. just really make it okay for them that they should speak up, because I've had plenty of students who don't speak up and then you're left with a mess to clean up afterwards. Pedal position. It's really important that the student is able to reach all of the controls, not just the pedals, but reach all of the controls and move them fully and freely. When you actually do this lesson, you're going to sit in the airplane for probably about 15 minutes, just showing them how everything moves and making sure that they can see outside, making sure they can reach everything. But what you want to make sure is they can push those pedals fully, freely all the way, and the stick can move to all four corners if there is such a thing. Okay, so that's really important. And followed closely by cushions. Me, myself, I sit on 2 cushions. If I don't sit on those cushions, I can't see anything and I fly terribly. If I fly terribly without cushions, a brand new student is certainly going to fly terribly. So what you want to get to know is, should they be sitting on any cushions? Take a few on the very first flight or on the taxi lesson and just sit them on them, and just, you're a better gauge than they are, but just see where their eye level is. Are they actually able to see out there, or are they way down here having to peer over the top? You need to know that. However many cushions you think is necessary, or they think is necessary, they should take those on every single flight afterwards, because if you change this, it changes what all the nose attitudes look like. It'll be really hard for them. There are particular cushions I like to use as well, so you can't be too fussy sometimes, but yeah, just always think about that. But when you get to that door there, you make sure they've got those cushions, because honestly, brand new student, if they don't have the cushions at all, then you just about cancel the flight, because the flight is not going to go well. And you're asking them in these flights to memorize what the different attitudes look like. It's going to be different if they're kind of not on the cushions that they normally sit on. Looking out, just really highlighting again here that we're looking out for other traffic and hazards, cloud and terrain, thinking about airspace whenever we're flying. Now, a large part of this I will do as the instructor today, but I'm going to transfer the responsibility for this over to you over the next couple of lessons. So you're letting them know, hey, this is what I expect in a couple of lessons' time. So as an instructor, you make sure all the areas are clear before you demonstrate the role, the pitch and the yaw and so on. And yeah, I've already discussed this next point. So here's your summary table. So it should just be questions at this point, okay? There's nothing on this slide that you need to teach. And if you're doing a pre-flight briefing, just before you go flying, this is really all I would draw up for the pre-flight briefing. I might actually, are we missing anything? No, we've got, so you'd have stick in here, ease the stick back and forward, primary effect, secondary effect. That's all I would draw up on the whiteboard and ask them to tell you the answers, or get them to draw it, and you can sit down and make them stand up for the next 15 minutes. And that's your primary effects. So keep it simple. The best advice I can give you is keep it really simple. Just the most simple and practical terms possible. Let me see if there's any additional instructional stuff I want to run through. The reason, if we go back to the elevator slide, where's the mouse gone? Elevator, where is it? Is that elevator? Yeah. So when I got to this slide, I mentioned to you that I don't talk about how deflecting the surface up reduces the angle of attack and reduces the camber, because some surfaces are actually symmetrical when they're not deflected. So actually, if the horizontal stabilizer is symmetrical, when you deflect the surface up like that, you are increasing the angle of attack. You are changing the angle of attack. It's just becoming a negative angle of attack. So get away from that, because that's not practical. All you really need to show here is, or speak about here is, when you deflect the surface upwards, it creates a downwards force which pitches the nose up. See how that's a lot more practical? It's the only one where I get a bit apprehensive about talking about angle of attack and camber reducing. It does, but it's not as easy to understand. An alternative explanation would be elevators deflected up, airflow is deflected up. The opposite response is a force downwards. Not as simple though. No, that's everything. Okay, do you have any questions about that? So I realise it's, even for you guys, it's probably information overload and just the instructional techniques, but at least you've got the background knowledge. It's just a case of thinking, okay, what do I need to say on each of these slides? So you just rehearse that. Any questions? All right, I think we're here until 2, aren't we? What's the time? I think what we'll do, just because Jess is away and she offered to do this briefing next Friday, is we actually might just do this briefing, but take a 10-minute break. And the briefing will only take about 30 minutes, I would say, so we might as well just get it done, and that saves Jess a task for Friday. So take 10 minutes if you're happy with that, and then we'll come back in and we'll finish the ancillary briefing, eh? Sorry, you had no questions, eh?